and then some will be read and write. So for example, if we wanted to know what the default is for the clock speed if you're using the internal clock, we would look for IRCF2 through IRCF0. And here we are, IRCF2, 1, and 0. So the default is 100. So the default is 100. Again, these are listed IRCF2, 1, and 0, starting with the MSB. So this is our default here, and sure enough, there's our 1 megahertz, and it even notes that for us here, note 3, default output frequency of oscillator on reset is 1 megahertz. So we'd like to speed that up to the 8 megahertz. So what we're going to do in code is we're going to type oscon bits.ircf2, oscon bits.ircf1, and oscon bits.ircf0. So let's do that. And we'll do copy and paste to make our lives a little bit easier. IRCF1 and IRCF0 is assigned and let's comment that. So we're going to set the internal clock to 8 megahertz. So what settings are we going to use here? Well, referring to our data sheet, IRCF 2, 1, and 0, if we want the clock to be 8 megahertz, those have to be 1, 1, 1. So we're simply going to assign those bits to 1, 1, and 1. And that will set our clock as the very first thing the program does when it starts to execute to 8 megahertz. And now the next thing for us to do is set our tris registers, our tri-state registers that is, to input for our input pins. So that's going to be these 4 here, RA0, 1, 2, and 3. And then to output for our 8 output pins, which is going to be RB0, 1, 2, and 3, and then RD 4, 5, 6, and 7. So you might remember from the Blink demo board we set our tris B bits to be output. So now we're going to set our tris A bits to be input. So we're going to enter tris A bits, and again, if you're interested in additional information pertaining to the tris register, or suppose we didn't know about the tris register to begin with, we would look under I/O ports, and you might be wondering how in the world do we set these to input or output. Well, in this description here, you're going to see it almost immediately mentions the tris register. And also, as we took a look at last time, we copied out to the desktop this P18F4550 header file. Let's go ahead and open that with Notepad. And that's another way that we can check our tris registers. So if we search for tris A, and sure enough, there we are. Here's tris A, the entire register, or tris A bits. And then tris A 0, 1, 2, 3, etc. So between this .h file and the explanation in the datasheet, we'd be able to discern that we want to type the following to make these pins here input. So we're going to type tris A bits.RA0 is assigned 1. Of course, 1 is for input, 0 is for output. And then we're going to copy and paste that to make our lives easy. So tris A bits.RA1, RA2, and RA3. So set pins for pot and switches to input. I'll add a few more spaces here. And now we're ready to set our tris bits for our output pins. So similarly, we're going to type tris B bits .RB3 is assigned 0, and again, copy and paste to make our lives easier. And then we're going to have tris D bits .RD 7 is assigned 0, and again this is following directly off of our diagram here. So we're going to want to set tris-B bits 0, 1, 2, and 3, and then tris-D bits 4, 5, 6, and 7 to output. And we're going to do that by assigning the tris register to a 0. So again, copy and paste to make our lives easy. So that's going to be RB3, 2, 1, and 0. And then for tris-D, we're going to set tris-D bits.rd7, 6, 5, and 4 to 0. So let's go ahead and comment that. So we're going to set pins for LEDs 0 through 3 to input with those 4 statements. And with these 4 statements here, we're going to set pins for LEDs 4 through 7 to input. Okay, now that our tris registers are configured for our digital inputs, we're going to get to the analog to digital converter configuration, which is more substantial and give us a much better chance to practice working with special function registers within the 18F4550. So suppose we hadn't done analog conversion with the 18F4550 before and we didn't even know where to start. Well, again, we would go to the datasheet and we could either search at the top here, or we could go down our table of contents and we would find pretty quickly here section 21, 10-bit analog to digital converter module. And the first thing that the analog to digital converter section does, well, it gives you a quick verbal description, or written description rather, but it immediately almost lists the control registers. And ADCON 0, 1, and 2 are the 3 control registers that we're going to set before we perform the conversion to get the conversion to give us the results that we're trying to achieve. So similar to the ASCON register, the 3 control registers have a table where each of the bits, what they are and what they do, is described, and then you're instructed on how to set them to get the A-to-D converter module to perform the conversion that we need it to. So let's start with the ADCON 0 register. So as we start with the MSB and work towards the LSB, we see the first 2 bits are unimplemented, so we don't have to worry about those. Then the next bit here, so this is bit 7, 6, and 5. So bit 5 is CHS3, and then we have CHS2, CH1, CHS0. So what are those all about? Well, if we look down here, we see that those are the analog channel select bits. And you'll notice that channel 0, 1, 2, etc. Here the datasheet mentions AN0, AN1, AN2. That might look familiar to you from the circuit diagram. What those are is those match this here, AN0, AN1, AN2, AN3, AN4, etc. So in other words, we have our analog input going to pin 2, which is AN0. So we want to set CHS 3, 2, 1, and 0 so that our analog channel is 0. So we're going to set CHS 3, 2, 1, and 0 to 0, 0, 0, and 0. Now in this particular case, it just so happens that the default values of those 4 bits already is what we're going to set it to, so if we didn't set it, it wouldn't matter, but it's better not to rely on the defaults for 2 reasons. One, code is more readable if you don't leave things as the default, and secondly, you never know, in a more substantial sized program you can set things, if you're talking about something that's thousands of lines, and then much later on you might have a different function that calls something else, and it gets confusing, and you might not remember what you said earlier. So it's definitely best to set these kinds of values explicitly. So let's go ahead and do that. So we're going to type ADCON 0 bits dot CHS3, and most of the time the name in the data sheet here, ADCON 0, and then simply appending lower bits in lowercase rather, and then dot, and then the name here will be what we'll use in our C syntax. If we ever were wondering about that, we could always check the .h file. So for example, if we go back to the .h file and to the top, and then we search for adcon 0, sure enough, there it is. And here we are down at the bottom, adcon 0 bits. And then so we're going to use a dot to refer to this inner part of the structures and the unions, how they have them set up. So adcon 0 bits dot, and there they are, CHS 3, 2, 1, and 0. Of course the order is reversed because in C, when you list structures, you start with the LSB effectively and you work towards the MSB, whereas the PIC datasheets traditionally do it the other way around, but you get the idea. So let's go ahead and set those first 4 bits. So that's going to be adcon 0 bits dot CHS 3 is assigned 0. And once again, we'll copy and paste to make our lives easier. So we're going to comment that as set analog channel to AN 0, which, as we can see from our diagram, just happens to be also port RA0 or pin 2. And since we wanted to set all those to 0, we don't even have to change the values that we're assigning to here. We can leave those all as 0. We do have to change CHS to 3, 2, 1, and 0. So we've now set our first 4 bits. Now the next 2 bits in the adcon 0 register, go done and A to D on, we're going to come back to those later. Go done actually starts the analog to digital conversion process and checks that it's complete. And A to D on we're going to enable after we've configured the other 2 A to D control registers. We'll get to that in a moment. So now let's look at adcon 1. So we have this nice table here for adcon 0. If we continue down, it's a pretty safe bet. We're going to find a table for adcon 1, and here we are. So the first 2 bits, just like adcon 0, the first 2 bits are unimplemented. And then we have 6 more bits that we're going to set. So VCFG1 and VCFG0, and then PCFG 3, 2, 1, and 0. So what is VCFG1 and what is VCFG0? Those are voltage reference configuration bits. So what the datasheet is trying to tell us here is that if we set this, we can set these to a range other than power and ground. So for example, we have our potentiometer configured here so that the highest possible voltage it could read is 5 volts and the lowest possible voltage it could read is 0. In some cases, you might want to use a different range than that, but we don't in our case. Going from power to ground is fine. So the voltage reference configuration bit for the negative source will set this bit to a 0, and that will use ground as our low-end reference. And then for our high-end reference, we'll set this bit to 0, and that will use power as our high-end reference. So we're going to type adcon 1 bits dot VCFG1 is assigned 0. And then we're going to type adcon 1 bits dot VCFG0 is also going to be assigned 0. So that's going to use power and ground as our limits for our high and low end voltage for analog input. And again, just through luck in this particular case, the default of those 2 values